In deep learning, performance is often treated as a function of complexity. But on recent benchmarks, complex architectures were outperformed by a single straight path. In 2022, a basic linear model called DLinear defeated informer class transformers on long-horizon forecasting tasks, reversing the assumption that deep always means better. The success of this model rests on a single preprocessing block called series decomp. Series decomp is a moving average, the same operation 1919 actuaries called graduation. To understand how this simple mechanism broke modern benchmarks, we have to trace the 100-year engineering lineage of the moving average. Every time series smoothing model developed since 1904 is a different mathematical answer to one question: how should the votes of past observations decay? In the early 1900s, actuaries needed a way to smooth jagged mortality tables. Without smoothing, life insurance premiums would fluctuate wildly between ages, based on noise in the raw data. We can test these early smoothing methods using the classic air passengers dataset. It's a classic record of monthly airline travel from 1949 to 1960, and it provides a clear ground truth for testing how filters isolate trends. The most basic tool is the Centered Simple Moving Average, or SMA. It replaces each data point with the equal mathematical average of its neighbors. When we apply an SMA with a 3-month span, the aggressive seasonal sawtooth pattern remains. At a 7-month span, the spikes begin to fade. By a 13-month span, the sawtooth vanishes entirely, leaving a smooth growth trend. This happens because a 12-month repeating cycle creates a frequency null in a 12-month average. The calculation is mathematically tuned to annihilate that specific repeating signal. Frederick Macaulay's 1931 work on graduation proved that moving averages aren't just blurring tools. They are filters that precisely select which frequencies survive. In real-time forecasting, we cannot use centered averages because we don't have access to future data points. We are forced to trail behind the trend. This introduces a physical constraint. Noise suppression is always bought with phase delay. On a noisy sine wave, a trailing SMA with a large window creates a smooth line, but it drags the signal significantly backward in time. Plotting this trade-off reveals the limit. As the window grows, roughness falls quickly, but the lag climbs at a rate of k-1 divided by 2. This lag is a significant operational risk. A smooth filter predicts a peak only after the ground truth has already started to fall. The challenge for engineers is to achieve smoothness without the extreme phase delay of an equal weight average. In 1904, actuarial formulas began to shift the votes of the data. They stopped giving every historical point an equal say. On a sudden dataset jump, a 9-step equal weight SMA reacts slowly, lagging as it climbs. But a linearly weighted average reacts faster, snapping to the new level several steps ahead of the SMA. This weighting shifts the filter's center of mass forward, artificially shortening its memory while maintaining the same physical window. While this reduces lag, it creates a new problem. The computer must now store and process an array of past values for every single calculation. By 1956, the U.S. Navy needed to track thousands of inventory items. Storing entire arrays of past values on punch cards or early tape drives was a massive computational burden. Robert Brown solved this with the exponential moving average, or EMA. It creates a weighted average with a window that effectively extends back forever. The math uses geometric decay. Today's smoothed state is simply a fraction of today's observation plus a fraction of yesterday's smoothed state. The decay profile is controlled by the alpha parameter. A high alpha creates a steep drop-off, hugging raw data, while a low alpha creates a long, slow memory, providing a heavy, delayed smooth. The breakthrough of the EMA was its efficiency. It provides the smoothing power of a weighted average while requiring the computer to store exactly one number in memory. However, Brown's single EMA had a flaw. When data has a consistent upward slope, the EMA will never actually catch the trend. On a trending line, the single EMA settles at a fixed distance below the real data. The gap is mathematically determined by the slope and the alpha value. To fix this, Brown and Charles Holt introduced double smoothing. They applied a second EMA to the first to measure the speed of the lag itself. By adding that measured trend back into the level, the model produces a line that tracks the upward trajectory perfectly. This ability to track level, trend, and seasonality with recursive states formed the Holt-Winters family, which remained the standard for operational forecasting today. Now, we can look back at the DLinear architecture that outperformed the transformers in 2022. Inside DLinear, the raw data is physically split into two signals: a smooth trend extracted by posed in 1931. Graduate the data to find the trend, then study the deviations. DLinear then fits one linear map to the trend and a separate linear map to the seasonal oscillations. Complex deep learning models often spend enormous computational effort trying to learn cyclical patterns from scratch. DLinear steps this by using a moving average to isolate those patterns before the learning even begins. When a simple moving average block helps a linear model out-forecast a transformer, it proves that the mathematical principles of data smoothing are a prior that never expires.